Now let's spend a few minutes here exploring the Lorentz transformation. To start, let's remind ourselves where we were and what we ended up with. The goal was, if we have, again, Alice, in this case, being stationary, her frame of reference, Bob going by at some velocity v. Of course, Bob in his frame of reference, he's stationary. He sees Alice moving the other direction with velocity v. And our goal was to have a simple set of formulas such that given coordinates of an event in Bob's frame of reference, xb, yb, zb, and tb, we could easily transform those into the equivalent coordinates for that given event in Alice's frame of reference. And obviously we're not going to redo the derivation here, but to remind you where it came from, we had an argument such that the form of the equations had to be linear. And what that meant was that we couldn't have any, given xb, yb, zb, and tb, we couldn't have any xb squares or t squares or square roots or things like that. The reason being, the argument we put forward is that if you have, let's consider time, okay, so say ticks of Bob's clock, they're equally spaced, 1 second, 2 seconds, 3 seconds, 4 seconds. Now when you transform time into Alice's frame of reference, as we know, there's this time dilation effect. So potentially the distances between ticks can change, but we should have uniformity there. In other words, if Bob's ticks, just as an example, are 1 apart, 1 second, or whatever unit of time we're using, 1, 1, 1, 1, then Alice could be, between her ticks, 1.5, 1.5, 1.5, but we can't have something like where Bob is 1, 1, 1, 1, Alice is 1.5, 1.8 between the next tick, 2.3 between that tick, and so on and so forth. So the distance between ticks when you do the transformation has to be the same. And you can make a similar argument for the measuring system for lengths, that you can have differences between Bob's length scale and Alice's in terms of a length contraction effect, as we've seen, but you can't have non-uniformity where Bob's measuring system is uniform and then it transforms into a non-uniform system in Alice's, because you get inconsistent results that way. So that was sort of a hand-waving argument, not a rigorous argument, but the idea was that then we had to have something like this form where G, H, M, and N were unknowns. We would like to find out what those were. And so we took these equations and plugged them into our invariant interval equation, which we had previously derived for the situation where you have essentially two frames of reference, or really multiple frames of reference. The invariant interval is invariant, is constant for all frames of reference. So we knew that was true. Plugged these in here, did a lot of algebra, and got these results here. That TA, given xb and tb, TA was gamma v over c squared xb plus gamma tb, where gamma, of course, is our Lorentz factor, and x sub a, gamma times x sub b plus gamma v t sub b. We rewrote those. We just moved things around a little bit and put them in this form for TA and XA. It's a little bit easier to memorize them in that form. TA equals gamma TB plus V over C squared XB. XA equals gamma XB. So notice this sort of parallelism here between TA, TB, XA, XB. Slight difference in the second term in each. I've got VTB over here in the XA and V over C squared XB. Part of the reason for that is the units have to work out. Here we've got to have units of length, and a velocity times the time gives us units of length. Here we have to have units of time throughout the whole thing. So a velocity divided by another velocity squared times a length, if you work that out, will give us units of time. One thing we didn't mention last time we were doing the derivation, we were concentrating really on XB and XA, TA, and TB, was what happened to YA, YB, ZA, and ZB. Well, remember last week when we did the analysis and showed that you don't have any width contraction effects or height contraction effects, and therefore in the perpendicular dimensions, if our direction of motion is in the x direction, then the y and z directions, there are no length contraction effects, width contraction, height contraction, radial contraction effects, and so those equations are very simple if we were doing something in 3 dimensions. And of course, normally we're just working in 1 dimension for simplicity. So Those are our Lorentz transformation equations. What we want to do now is rewrite them slightly and then investigate them a little bit to see what the math is telling us here. It's also a good idea to not just say, okay, there are the equations, let's go use them, but to understand them better, find out what they're telling us, whether they're consistent, maybe we made a mistake someplace, and so on and so forth. So to do that, let's rewrite them up here in slightly different form, because these are A's and B's, and sometimes it's easy to forget who's moving here, who's stationary, and so on and so forth. So in our derivation, we assumed this was from the perspective of Alice being stationary, Bob moving with velocity v. We'd like to have similar set of equations for what about Bob's perspective? If he considers himself stationary, then Alice is moving in the other direction with velocity v, negative v in essence, in the negative direction. And therefore, what would the equations look like in that case? So let's, first of all, rewrite these. And so instead of A for Alice, we're going to have rest for the frame of reference that's considered to be at rest. So we'll have something like this. We'll say T, let's get a better pen here, T rest equals gamma still being the Lorentz factor. TB is our moving frame, so we'll just say T moving plus V over C squared X moving. Okay, so those that in this case would refer to Bob, and then X rest equals gamma X in the moving frame with respect to Alice. Okay, Alice is being assumed at rest here, plus V T moving, not rest. Okay, so there's, we got that. Now, I should say another way we could have labeled these, and you want to choose a way that makes sense to you. Often we'll say we've got the rocket frame and the lab frame. And in many textbooks you'll see it that way as well. So if you prefer that, you could certainly use it. So instead of the rest frame, that would be the lab frame, and then the moving frame is the rocket frame. And sometimes that's even a little easier because then you can visualize, you can picture, okay, I've got the rocket and I've got the lab, the observer, Alice in this case, in the lab. So you can either use lab and rocket or rest and moving there. Well, what we want to do in part one of exploring this is focus on this equation here and just see what happens when we put in some different values here, see if the results make sense based on our previous understanding of what we've been doing with things like length contraction and so on and so forth. So to start off, what happens if, let's just say, let v equals 0. What if the velocity is 0 here? Well, we know if the velocity is 0, then gamma, just remind ourselves gamma, 1 over the square root of 1 minus v squared over c squared. So if velocity is 0, gamma is 1. So we know gamma equals 1 in that case. So what does this equation become? Well, we get x rest, Alice's perspective, gamma is 1 here, equals x moving, and v is 0, so this is 0 as well. So we just get x rest equals x moving. In other words, if we were thinking about the, again, lattice of clocks here is the underlying foundation of our observations. Alice has her lattice of clocks, and that's her measuring system for length and time. Bob would have his as well. If v is 0, they're not moving with respect to each other. So any measurement that Bob makes here, out here Bob says, okay, in his moving frame, I see something at xb, or in this case we're calling x moving, the moving frame at 23.8. Well, since they're stationary with respect to the other, Alice would also see that on her system as 23.8. So that's what this is telling us, and we hope we get this answer, otherwise something went wrong along the way. So that's one simple check we can do. What happens if, let's just get some room here. So that was our first test case. That made sense. Now let's say, let's let let's not let v be equal to 0, but let's make it really small compared to the speed of light, sort of everyday type of velocity. So if v is much less than c, then gamma is approximately equal to 1. Right? If v is much less than c here, this is essentially 1 minus pretty close to 0. 1 divided by the square root of pretty close to 1 is going to equal 1. So gamma is approximately equal to 1. And so what do we get then? So we get x rest equals gamma, let's say, is approximately equal to 1 here. And so it becomes x moving in the moving frame. And by the way, just again, the terminology here, this does not mean x is moving. This belongs an x coordinate, an x measurement in the moving frame. Okay, so just fix that in your mind. Don't get confused about that. So x rest equals x moving here plus a velocity. Okay, it's going to be non-zero. It's going to be much less than c, but still non-zero, times t in the moving frame. In other words, on one of Bob's clocks in the moving frame. Well, what does this remind ourselves of? Hopefully, it reminds ourselves of the Galilean transformation, especially because if we go back up here for a minute and look at the t equation, if v is much less than c and gamma equals 1, look what we have here. Gamma, of course, being 1. If v is much less than c, this is a very small number, v divided by c squared. Not just v divided by c, but v divided by c squared. That's a very, very small number. And essentially, we just have time in the rest frame equals time in the moving frame. And therefore, this is just t. And so that would make this a Galilean transformation, where t is the same for all observers, all frames of reference, and you just have your basic x in the rest frame equals the x value in the moving frame plus v times t. Essentially, this shows how far Bob has moved along. And so if he measures something, again, say at 23 out here on his lattice of clocks, his measuring system, but he's also moved a certain amount, then the distance to Alice, the x in the rest frame, is the amount Bob has moved plus the amount he measures out to 0.23 on his measuring system. And so basic Galilean transformation there. So that checks as well, because we know that works in our everyday experience when velocities are much less than the speed of light. Okay, so now though, what happens when we have velocity being large? Let v be large. Obviously not equal to c, but up there someplace. So let v be large. Then what do we have? Well, essentially we just have this equation. We can't do any simplifications of it. But let's split it apart here and take a look at it. So we've got x in the rest frame. X in the rest frame equals gamma times x in the moving frame plus gamma times v times time as measured in the moving frame, in Bob's frame there. All I did was multiply that by gamma and then that term by gamma to split it apart here. So essentially this is very similar to the Galilean transformation which we were just talking about. In other words, for Alice here, Bob is going to measure some event at some x value in his frame. Maybe it's at 23 again on his lattice of clocks and his measuring system out there. So where is that going to occur on Alice's lattice of clocks? Well, it's going to occur, again, the general idea is how far has Bob moved, what time is the measurement being made, and then plus whatever he's measuring out here. We're assuming it's a positive value. So we're assuming he measures it at 23 out here, but in the meantime, he's also moved over here, and so the distance for Alice will be that distance plus that distance. So this looks similar to the Galilean transformation, same concept, except we've got these gamma factors in here. And in fact, if Bob is measuring this at his time t equals 0, and we also assume that they're right together at t equals 0, Bob is just passing by Alice at t equals 0. So if we're measuring this at t equals 0 for Bob, t moving equals 0, then this term goes to 0, and look what we're left with here. That's our length contraction equation. In other words, what that is saying is if Bob says, okay, right at t equals 0 on my clock, I measure out, I see something at 23 out here. Alice, remember, length in the moving frame is going to be contracted. So Alice here will see x moving as less than her value for whatever the distance is, 23 or whatever. Okay? So another way of saying this, the way we wrote the equation before, was x in a moving frame equals 1 over gamma x in the rest frame, the stationary frame. Just to emphasize, because gamma is always greater than 1, greater than or equal to 1, of course, that means the moving value as measured by Alice in this case is less than, you take x rest, multiply by maybe gamma is 2, 1/2, and that you get a smaller value. So this is the length contraction effect, and essentially that's built into the Lorentz transformation, as it better be. If it isn't, then we've got something really wrong here. Either our original conclusion with length contraction was incorrect, or our Lorentz transformation derivation was incorrect. So what we see here is that, first of all, we can get the Galilean transformation out of this, that equation, for sort of everyday velocities, much less than the speed of light. We also see that when v is large, that we get the length contraction effect coming out of it, where again, length contraction in the simplest case is simply when Bob measures something at t equals 0, so he's there, Alice is there, Bob measures a certain length, and then Alice gets that length as well, and you get the length contraction effect going on there. So that's in there as well, and so that's exploring the x equation here. In our next video clip, part 2, we want to do a little bit of exploration of the time equation. Moving on to part 2 of the Lorentz transformation. We brought back one of our props here, taped it up on the board. We'll see what we're going to do with that in a minute. But in this part, we want to focus on the time equation, the time transformation equation. In the last video clip, we were focusing on the x location, the x transformation equation. So we have T rest equals gamma, remember rest frame and moving frame here. And we're measuring Alice is in the rest frame, Bob is in the moving frame, moving to the right at velocity v in the positive x direction. So gamma times a time value in the moving frame plus gamma v over c squared times an x value in the moving frame. In other words, x and t, the moving frame values, are measurements made by Bob. We want to transform that into a time value for Alice in this case. So just as we did with the last equation, let's explore this a little bit. Let's just say, let's just let x moving here, in other words, Bob's measurement of some event in the moving frame, let that equal 0. Okay, very simple. And then, of course, this term becomes 0, and we're left with t in the rest frame equals gamma times t in the moving frame, which should remind ourselves of the time dilation equation, because that's exactly what it is. Does this make sense? Well, remember, when we derived the time dilation equation, we used the light clock. And the light clock in the frame here, in Bob's frame, okay, is just, beam of light bouncing up and down, like that in Bob's frame. He's carrying along with him. And Alice, of course, sees it at a diagonal, and that's where we get the time dilation effect. But as far as Bob is concerned, if he's carrying the light clock with him as it goes along, that bouncing up and down is happening in his moving frame, what we're labeling the moving frame from Alice's perspective, but in Bob's frame at x equals 0, okay, because it's in his cockpit with him, and that's his definition of the origin, right? As far as he's concerned, he's not moving. And so essentially, for that light clock example, we had the x value for Bob in the moving frame be equal to 0, and we see it falls right out of the Lorentz transformation equation as it should. We just get t in the rest frame, time measured in the rest frame is gamma times the time measured in the moving frame. Gamma is greater than than 1, greater than or equal to 1, of course. And so the way we wrote it previously was something like this. We said time in the moving frame equals 1 over gamma times time in the rest frame. Obviously, you can write it either way there. But this emphasized, for us at least, the time dilation effect, gamma being greater than or equal to 1. So the elapsed time in the moving frame is slower than in the rest frame. Moving clocks run slow was how we termed that. So Lorentz transformation equation for that checks out. It gives us our basic time dilation result that we derived earlier. Now, though, let's say, what if we just let x moving be anything here? So this is where we come back to Alice here. So we can't simplify our equation at all. We're assuming that v is some value. I guess we could say certainly if v is 0 here, as we did before, then gamma's 1, and you just get time in the rest frame equals time in the moving frame. In other words, both Alice and Bob are sitting there with their clocks. They're not moving with respect to each other, and they measure the same time. So that's a trivial case there. But what about the general case where Bob is measuring some time in his moving frame, and again, of course, he's not considering himself to be moving. This is from Alice's perspective in his frame, and an x value in the frame. Well, let's imagine the situation then. Alice is here. We'll put her in a spaceship, but we'll assume she's at rest. Let's bring back Bob in his spaceship, each with their lattice of clocks, each of them synchronized in their own frame of reference. And as we've drawn it here, of course, Bob is moving like this. And so let's imagine that right about, let's get this lined up here a little bit, right about here, obviously he probably would have traveled much farther than that, but that Bob observes a certain event. Actually, let's not even do it that way. Let's say that Alice, at an instant in time on her clocks, sets off photographs all along her lattice of clocks. And she photographs not only her clocks, but the corresponding clocks of Bob, wherever he happens to be at that instant in time. Okay, and let's just say it's 10 seconds. Okay, so on Alice's clock. So at 10 seconds, Bob is flying by here when they're right next to each other. Both their times say t equals 0, ta equals 0, tb equals 0. And then later on, at some point, way down the line, of course, but we won't show that. We'll just imagine about right here. 10 seconds have gone by. Alice takes photographs at all her clocks at that instant in time. The question is, what are the readings on Bob's clocks? And we're not going to put numbers in here. We just want to get a qualitative sense of this at this point. So let's imagine it's something like that there. And note one thing about our equation here is that, let's say, we've got a time right here. These are all 10 seconds reading on Alice's clock. So we've got 10 seconds on that one. What is the value of the corresponding clock right here going to be on Bob's clock at that instant in time? Well, according to the Lorentz transformation equation here, if this is 10 seconds over here, according to Alice, I've got something plus something over here. And assuming both those terms are both positive terms here, we're assuming nothing is 0, because v is not 0, gamma is not 0, obviously. X is not 0. In other words, the x value is maybe 1, 2, the third clock out there, the second clock, or something like that. So what that essentially means is if this is 10, then this term here has to be less than 10. And in particular, t moving has to be less than 10. In other words, the time on Bob's clock, whichever one you point to out there, has to be less than 10. And that, again, is an indication of the time dilation effect, that the moving clocks are going to run slow. They're perfectly, at least the clocks right here at t equals 0 said, fine, everything was set up, not all the clocks, but just the clocks at t equals 0. But down here, as it went on, we find when Alice took the photo that the time on, say, I guess I've been pointing to the second one there, whichever one I've been pointing to, time has to be less than 10 because gamma's greater than 1. This term also is positive, and therefore the value of time on Bob's clock in the moving frame has to be less than 10. Okay, so that's sort of an interesting result. It just reminds us of time dilation. But now let's also think about something else, because remember, Alice took pictures along the whole line here of her clocks. And so 10 seconds on this clock, and we can read off the value on Bob's clock at that instant in time. And then what about the next clock over? Also 10 seconds for Alice. So again, this is 10. But note what happens as we move over one clock. The X value here in Bob's frame also gets larger by whatever amount it is. We could use our other equation to get that. We're interested more in the qualitative argument here. So as we move this way, so 10 seconds on this clock, some value on Bob's clock that's less than 10. As we move this way, let's just say it's 8. Give us a number here. So say it was 8 seconds on Bob's clock for that one. As we move this way, this value is getting bigger as we move from that clock to that clock. Therefore, for the next clock over, this has to be even less. If this was 8 for this clock, then when we move it one over, this term is getting a little bit bigger. This term has to get a little smaller. So this has to be a little smaller than 8 now. And if we move over one more, still 10 seconds on Alice's clock, so this is still 10, but this term's getting a little bit bigger even, and therefore this has to get a little smaller. So as you move in this direction, again, all Alice's clocks are 10 seconds, but Bob's clocks, the time as Alice observes them through her photos here that she's taken, the time on these things is getting smaller. It's really prior in time. Again, if this was 8 seconds, this maybe has to be 7.6, and then the next one over is 7.2 or something like that as it goes on. And what that means is this is another verification of something we've talked about before, and that is leading clocks lag. Okay? In other words, leading clocks lag is built in to the Lorentz transformation equation through this term right here. Because otherwise, put this down for a minute, otherwise this sort of looks strange because the Galilean transformation, we just had, TA equals TB, T rest equals T moving. There was no change. And so we'd expect, okay, special theory of relativity, gamma is going to be involved. So we might expect something like T rest equals gamma T sub moving without this term here. And we can sort of get a handle on that. But then this term is just weird. We say, how does that work in terms of not only an effect on time here, but you're adding some distance in here, as it were, in a sense, a distance factor that's affecting the time observed in Alice's frame of reference compared to Bob's frame of reference. And what this term essentially is doing, that another way to put it, is leading clocks lag. As we were just trying to argue here, is that, again, Alice takes all the photographs at t equals 10 seconds. So all her clocks say 10, but maybe Bob's clock here, because I've got two terms here, they're both positive. If this is 10, that has to be less than 10. We said maybe it's 8. But then as you move over one, this is getting bigger. You're moving in more positive x direction there. And therefore, if this is 8, that's got to be 7.6 or something like that. Move over again, got to be down 7.2 now, because this term keeps getting bigger. This term has to keep getting smaller. Again, we don't see these effects, at least not in everyday life, because look at the factor here, not only gamma, of course, but v over c squared. This is a very, very small number. So it does show that leading clocks lag, and in fact, in a later video clip, we're going to look at that in a more quantitative fashion to figure out exactly how much do leading clocks lag by. But this isn't showing, therefore, that the time equation, as part of the Lorentz transformation equations, has this built in. Not only the time dilation effect, which we got from our light clock, but also the leading clocks lag effect as well. So that's part 2 of exploring the Lorentz transformation. In part 3, we're going to look at the case where, what about from Bob's perspective, looking at Alice, or in general, what if we have some frame of reference moving to the left instead of to the right? Part 3 of exploring the Lorentz transformation. Here are equations back again, and I've changed them back to A and B for Bob and Alice because we're going to write a new version of them up here, and it will be easier to see what's going on if we're thinking about Alice and Bob again. But of course, we can think about the rest frame and the moving frame, or lab frame and rocket frame, if you want to think about it that way, where Alice in this case would be the rest frame or the lab frame. Bob would be in the rocket frame, that is moving with respect to the lab with positive velocity v. And the question is here, really two-part question, essentially the same question, just asked in two different ways. First one is, what happens in terms of Bob looking at Alice? Bob thinks he's stationary. That's his perception. And it's Alice who's moving with constant velocity, but in the opposite direction, in the negative x direction. What would the equations look like in that case? Another way to say that is, what if we just turn Bob around and Bob goes in the negative x direction at velocity v? Then what would it be? But let's ask it in terms of the first version, in terms of, okay, now let's look at it from Bob's perspective. He's seeing Alice move with velocity negative v, essentially in the negative x direction, or we could say with velocity v in the negative x direction. And the key here is, because we could go back and say, oh, do we have to do that derivation again and go through and change any time the velocity appears, turn it into a negative sign and then see negative v and see what happens? And fortunately the answer is no. Even if it was yes, we probably wouldn't go through it all again. We just give you the result. But here's our basic equations that were derived on the assumption that the rocket frame, the moving frame, is going with velocity v in the positive x direction. If we have a velocity v in the negative x direction, all we have to do is change the sign any place we see v appear in our equations, because v is assumed to be a positive quantity here. So if we're just changing direction to the negative direction, it just becomes a negative v. And again, we'll assume the actual value of v here is positive. So by putting a negative sign in, that will just change the direction. And the other factor we have to remember is, well, v also is in gamma. So the good news there, though, is gamma, of course, square root of 1 minus v squared over c squared. V squared saves us in this case because, of course, if you take a negative number and square it, it turns into a positive number. So that whether v is negative or positive, gamma has the same value. Gamma does not change. So we don't have to worry about gamma. And the only changes that are made here are in these two plus signs. Instead of having a plus v over c squared and a plus v, I have a negative v over c squared and a negative v, or a minus v in each case. So we can write it like this. From Bob's perspective, we'd say, okay, TB for Bob is gamma TA minus v over c squared xa, and xb for Bob is gamma times xa minus v t a, like that. In other words, given x and t values in Alice's frame of reference, as she measures them, then we can figure out what the values would be in Bob's frame of reference, just by putting the minus signs in there. So that gives us a sense of how we can go back and forth very easily. And it's probably useful to memorize one form of these, and perhaps if you like to use the terminology lab and rocket, because it's very visual that way. So if you think, okay, I'm going to have a rocket moving to the right in the positive x direction, and so therefore the b's here would be the lab quantities, and the a's would be, the b's here would be the rocket quantities, and the a's would be the lab quantities, if you want to think about that, or the rest frame quantities and the moving quantities. This assumes motion to the right, positive x direction. This version down here, essentially it says, now the b's are the lab frame of reference, the rest frame in this sense, because now Bob, sitting in his spaceship, is assuming that from his perspective, he's in the rest frame and the lab frame. And it's Alice moving, whether she's in the ship or not, she's moving to the left there. And therefore, you get the negative signs in there. Otherwise, it's the same form there. So as we proceed, we will explore more of the implications of this. This week we'll do a little bit more quantitatively, again with leading clocks lag, but then as we move forward we'll start actually reintroducing space-time diagrams, and not this week, but next week, and then also getting into some of the paradoxes involved with the special theory of relativity that the concepts and equations we've developed so far lead us into, and so we need to figure out some of those things. But before we get into that, we have few more things to do for this week.